Hi, and just today we are gonna discuss the Routh array, or which is also called as the Routh criterion, which is used to predict that whether our system is stable or unstable. So this is regarding Routh array, or which is also called as Routh criteria, and this is used to determine that whether a system is stable or unstable. So basically here in this case we have the characteristic equation in S domain. So if our characteristic equation is in the form of a naught s to the power n plus a1 s to the power n minus 1 plus a2 s to the power n minus 2 up to an is equal to 0, then we need to construct the array in the following manner. So this is s to the power nth row, s to the power n minus 1th row, s to the power n minus 2 row, and we are going to continue up to s to the power 0th row. And now in this case the corresponding elements in the row will be, here the coefficient of s to the power n is a naught, so we are going to consider a naught, we are going to neglect a1 and we are going to write a2, and we are going to neglect a3 and we are going to write a4, and the coefficient of s to the power n minus 1 is a1, so we are going to neglect a2 and we are going to write a3, and we are going to neglect a4 and we'll write a5. And now we need to find this element. Let's say that this element is a1, so in this case a1 will be equal to small a1 multiplied by small a2 minus a3 into a naught divided by the first element in this row, so this will be a1. And in order to find this element, let's say this element is a2, so we are gonna delete this particular column for time being. So this will be a2 is equal to a1 multiplied by a4 minus a5 multiplied by a naught divided by, and this will be a1. So in very similar fashion we can find the rest elements in these rows, and here we'll get, of course this is 0 because we don't have any numerical value here in order to find this value. So now according to Routh array there are some rules which we need to follow to predict whether our system is stable or unstable. And the first rule is, if all the elements in the first column are positive, then the system is stable. And the second rule is, if any one value in first column here is negative, then the system is unstable. The third rule is, if any one value in first column is 0, then the system is marginally stable. And the final and important rule is, the number of sign changes in first column is equal to the number of roots with positive real parts that is the roots lying in the right half plane. Now in order to understand this rule number 4, if suppose here we got an element A0, A1, and this is capital A1, so these are the elements of the first column. And now if suppose we got negative A1 in the first column, and this is positive and this is positive, and now the number of sign changes in the first column will be, the first sign change is from positive to negative, and the second sign change is from negative to again positive, positive to negative, positive to negative, and the second sign change is from the negative to positive, so negative to positive. So there are 2 times the sign changes, 2 times sign changes in the first column, which implies that there are 2 roots with the positive real parts, that is the 2 roots are lying in the right half plane of the graph, and therefore the system is unstable with 2 roots which are lying in the right half plane. Now in order to get the deep understanding regarding the Routh array, we are going to solve some examples depending on this. So here we have our first question. And given the characteristic equation below, find the number of roots which are located in the right side of the imaginary axis. Means here we need to find the number of roots with the positive real parts which are lying in the right half plane. So here what we are going to do is we are going to construct the Routh array. So this will be our s to the power 4th row, s to the power 3 row, s to the power 2, s to the power 1, and this will be s to the power 0. The coefficient of s to the power 4 is 1, so we are going to take it. We are going to neglect 5, but we are going to take the alternate terms, -1, we are going to neglect -17, and we are going to consider 12. S to the power 3 is, the coefficient is 5, we are going to neglect the alternate terms, so 5 we are going to consider, we are going to neglect -1, we are going to consider -17, and we are going to neglect 12, so here we'll get 0. And now suppose this element is A1, so A1 will be equal to 5 into -1 minus -17 multiplied by 1 over the first element of this row is 5, so this will be equal to 5 into -1 minus -17 into 1 over 5, and here we'll get 12 by 5, so this will be 12 by 5. And now we need to find this element. Let's suppose this element is A2, so time being we are gonna delete this particular column, so this will be 5 multiplied by 12, 5 multiplied by 12 minus 0 multiplied by 1, 0 multiplied by 1 over the first row of this row is 5, so this will be 5 multiplied by 12 minus 0 over 5, so this will be equal to 12, and this element will be equal to 0 because we don't have any numerical terms in order to find this element. And now suppose this element here we have B1, so we are gonna find what the B1 is. So B1 will be equal to 12 by 5 multiplied by -17 minus 12 into 5 over 12 by 5, so this will be equal to 12 by 5 multiplied by -17 minus 60 over 12 by 5, so this will be equal to -42. And in order to find this element we are gonna delete this column, so this will be equal to 12 by 5 into 0, so B2 will be equal to 12 by 5 into 0 minus 0 into 5 over 12 by 5, which will be again equal to 0. So here we'll get 0, and here of course we have 0. And now we are going to find this element. So let's say that this element here is C1. So C1 is equal to negative 42 multiplied by 12 minus 0 multiplied by 12 by 5 over negative 42. So this will be equal to negative 42 into 12 minus 0 divided by negative 42. So here we have 12, and our first column is completed now, and we need to find the number of roots which are located in the right side of the imaginary axis. So the number of roots located in right side of imaginary axis is equal to the number of sign change in first column, and here we have negative sign, here we have positive, and here we have positive. So from positive to negative we have one time sign change, and from negative to positive we have another time sign change. So as there are two sign changes in the first column, so 2 sign change in first column implies that there are 2 roots lying in right half plane. So this is our answer. There are 2 roots which are lying in the right half plane, and our system is of course unstable. Our system is unstable because here we got the negative term in the first column. Now let's take the second example. Okay, here's the next example. Which of the value of the Kc for which the characteristic equation s cube plus 6x square plus 11s plus 6 plus 6 Kc is equal to 0 when the system is stable, when the system is unstable, and when the system is in the verge of stability? So our CH equation is s cube plus 6x square plus 11s plus 6 plus 6 Kc. Now we can write this equation as x cube plus 6s square plus 11s plus this whole term will be some constant c, suppose, equals to 0. Now we are going to construct our Routh array. So s cube, s square, s to the power 1 and s to the power 0. The coefficient of s cube is 1. We are going to neglect this term, we'll take 11, and we are going to neglect this c. S square 6, we are going to neglect 11, and c is 6 plus 6 Kc, and we are going to find this term. So our a1 will be equal to 6 into 11 minus 6 plus 6 Kc over 6. So this will be 66 minus 6 plus 6 Kc over 6. So this will be 66 minus 6 minus 6 Kc over 6. So this will be 60 minus 6 Kc over 6. This can be written as 10 minus Kc. So here we have E1 is equal to 10 minus Kc. And now what we are going to do is 10 minus Kc, we got the element in the first column, and when the system is stable we know that this 10 minus Kc should be greater than 0, as it must be all positive values. So here we know that we can write this equation as negative Kc should be greater than negative 10, but we need to find Kc, so we are going to multiply with negative sign. So negative Kc should be less than negative 10. So Kc should be less than negative 10 for stable condition. And in another case, if the system is unstable, then the value must be negative in the first column. So 10 minus Kc should be less than 0. So negative Kc should be less than negative 10, but we want to find the value of Kc, so we are going to multiply with negative sign. So negative Kc should be greater than negative 10. So Kc should be greater than 10 for unstable system, and in the verge of stability means 10 minus Kc should be equal to 0, then the system will be called as the marginally stable system. So this will be negative Kc should be equal to negative 10. So Kc should be equal to 10 for verge of stability. And now we are going to study the third example. I hope that you are familiar with the modification of the block diagram in the process dynamics and control. So here we have our third example. Consider the cascade control configuration shown below, and the system is stable when Kc is. So here we have the negative feedback system. So we are going to modify this diagram. So this will be something like this. We have S, we have another 0.5 transfer function, and this is the negative feedback system. So we are going to modify this block diagram, and this can be written as, okay, so this can be written as Gs is equal to Kc times S plus 2 upon S minus 4 upon, as it is the negative feedback, we are going to take plus in the denominator, plus Kc into S plus 2 upon S minus 4. So this can be written as Kc into, we'll call it as G upon 1 plus Kc into G. So this will be another transfer function. So Kc into G upon 1 plus Kc into G. And here we have our closed loop configuration. And now we are going to find the value of Kc for this. So again we can write this as, let us say that this is Fs. This should be equal to 0.5 into Kcg over 1 plus Kcg over 1 plus 0.5 Kcg over 1 plus Kcg. This can be written as 0.5 Kcg over 1 plus Kcg divided by 1 plus Kcg plus 0.5 Kcg 1 plus Kcg plus 0.5 Kcg over 1 plus Kcg. So this will get cancelled, and we are left with 0.5 Kc into G is S plus 2 upon S minus 4 over 1 plus Kc into S plus 2 upon S minus 4 plus 0.5 into Kc, G is S plus 2 upon S minus 4. And now what we are going to do is, we are going to simplify this equation. So this will be 0.5 Kc over S plus 2 upon S minus 4, and our denominator will be 1 plus, this will be, okay, we can modify this as 1 plus 1.5 Kcg, because here we have 1 and here we have 0.5, so we can write this as 1 plus 1.5 times Kcg. So this will be equal to 0.5 into Kc multiplied by S plus 2 upon S minus 4 divided by 1 plus 1.5 times Kc into S plus 2 upon S minus 4. So this will be 0.5 upon into Kc multiplied by S plus 2 upon S minus 4 divided by 1 plus 1.5 Kcs plus 1.5 into 2 is plus 3 Kc over S minus 4, and this can be written as 0.5 Kc into S plus 2 upon S minus 4 divided by S minus 4 plus 1.5 Kcs plus 3 Kc upon S minus 4. So this denominator will get cancelled, and our characteristic equation is, this can be written as S plus 1.5 Kcs plus 3 Kc minus 4 is equal to 0. So if we take s common, so this will be 1 plus 1.5 kc plus 3 kc minus 4 will be equal to 0. And if we construct the Routh array now, so this will be s to the power 1 and s to the power 0. The coefficient of s to the power 1 is 1 plus 1.5 times kc, and we are going to neglect this term, and s to the power 0 is k. So here we got 1 plus 1.5 times kc, and here they have asked that the system is stable, means this should be greater than 0. So 1.5 times kc should be greater than -1. So kc should be greater than 1 over 1.5. kc should be greater than -0.6666. And now what we are going to do is, in the given option, we are going to check that each term in this option should be greater, that the right answer will be the one which is greater than 0.6666. So here we have our first option, this is 4 over 3 and this is 1.3, but something is incomplete in our calculation, because here kc should be greater than -0.666 and here we have all the positive values. So we need to determine the value of this element. So this is 3 kc minus 4, and here in this case 3 kc minus 4 should also be greater than 0 for the stable system. So 3 kc should be greater than 4, so kc should be greater than 4 by 3, and this is for all the positive cases, and in the option we have all the positive values. So we are gonna check that 4 by 3 is 1.333. So the correct answer will be the one which is greater than 1.333. So 5 by 4 is equal to 1.25. So this is not the answer. This is also not the answer. So our correct option is 3 by 2, because as it is greater than 1.333, so the system is stable when the kc is 3 by 2. And now we are gonna solve another example which is dependent upon the Routh array. So here we have our question. The process with the transfer function gp is equal to 2 over s minus 1 is to be controlled by a feedback proportional controller at a gain kc. If the transfer function for all other elements in the control loop are unity, then the value of kc for the stable response is, and we are going to consider that we have negative feedback system. So here we have the negative feedback system, this is positive, and here we should get negative for negative feedback system, and we have the proportional controller gain is kc, and the rest elements are unity. So we are going to consider this transfer function gp 2 over s minus 1. This will be our final value y, and this will be the closed loop system. And now we are going to find the value of kc for stable response. So here our transfer function will be gs is equal to kc into 2 upon s minus 1 upon 1 plus kc into 2 upon s minus 1, and we can modify the denominator in order to get the characteristic equation. So this will be 2 kc upon s minus 1 divided by s minus 1 plus 2 kc over s minus 1. So the denominator get cancels, and the characteristic equation is s plus 2 kc minus 1 is equal to 0. And if we construct the Routh array for this one, so s to the power 1 and s to the power 0, so the coefficient of s to the power 1 is 1, and the coefficient of s to the power 0 is 2 kc minus 1, and for the stable system 2 kc minus 1 should be greater than 0. So 2 kc should be greater than 1, so kc must be greater than 1 by 2. So for the stable system, Kca should be greater than 1 by 2. It is important to note that in the question we have the rest of the transfer function are all unity, means if we have the transfer function for the final control element gf, and here we have the transfer function for the measuring element gm, but as these are unity, so we are not gonna consider them in a closed loop diagram. So this was all the information regarding the Routh array, and thank you for spending time with me.